All right, we're going to look at how to write conservation of energy equations. And in your notes, you're given this basic blank form that you can use, but to show you how to do this, I'm just going to go straight into the example. So your example is, we have a 2 kilogram ball that's released from rest on the track at location A. The height of the track at location A is h sub A is 3 meters. And if the ball is moving at a speed of 6 meters per second at location B, we want to know what is the height of the ball at that location. So when you're going to write a conservation of energy equation, the first thing you need to do is you need to identify the initial and final locations of the object in the problem. So in this one, it says the 2 kilogram ball is released from rest at location A. So our initial energy is going to be based on location A. And then it's asking for the height at location B. So this is going to be final. So when you're writing conservation of energy equations, or even doing any kind of conservation of energy calculations, we don't care anything about the middle. We only care about what kind of energy do we have at the beginning, what kind do we have at the end. So what I'm going to do is I'm going to ask 2 questions to figure out how to write this equation. Now, remember that the 1/2 mv squared is kinetic energy, and this would be our initial kinetic energy. The mgh is our potential energy, and this would be the initial potential energy. So we have the same thing mirrored for our final energy. So what we're doing is we are going to look at which of these we have available for initial and final. So the first question is it moving? So in the initial portion, is it moving? Well, it says the ball is released from rest. That means that it is not moving, which means it does not have kinetic energy. The next question is it above our designated h equals 0? Well, here's our h equals 0 all the way at the ground. So A is definitely above h equals 0. So that means in our equation, we would have mass times gravity times the initial height. And I can change this for the letter of my location. So this is the first half of our conservation of energy equation that is just showing our initial energy. Now we're going to look at what kind of energy do we have at location B. So again, is it moving? Well, it tells us that it is moving with a speed of 6 meters per second, so yes, it's moving. So we have the equation 1/2 m v final, or vb, squared. The next question, is it above our designated h equals 0? Yes. So that means it also has gravitational potential energy. So I'm going to write that down. So this is it. This is our conservation of energy equation specific to this question. We have our gravitational potential energy, initial, that's equal to the kinetic energy plus the gravitational potential energy at location B. So my next step is going to be to simplify it by plugging in numbers. So I am going to do my mass of 2 kilograms times the acceleration due to gravity times the height of 3 meters. And that is 58.8. And that is going to equal, sorry, I got interrupted. So we have 58.8 joules of energy initially. Now for our kinetic energy, it's 1/2 of the mass of 2 kilograms times the speed of 6 meters per second squared. So that is going to be 36. And we're going to add that to our gravitational potential energy final. Now, we know the mass is 2 kilograms, and we know we have G is 9.8, and we're looking for H, so I'm just going to leave that as a variable. And so I'm going to have 19.6 H. So this is my simplified equation that just has the numbers. So under the solve, I'm going to go ahead and write that down. I have 58.8 is equal to 36 plus 19.6h. Now we're going to solve this just like any algebraic equation. First, I need to isolate the term that has my variable in it, which means I have 19.6h plus 36. So to get rid of the 36, I'm going to do the opposite of adding, and I'm going to subtract it from both sides. And that is going to give me 22.8. So now I'm going to have 22.8 is equal to 19.6h. Now that I have my term with my variable isolated, now I need to isolate the variable. So right now it is being multiplied by 19.6. So my next step is going to be to divide by 19.6. And what I do to one side, I have to do to the other. So 22.8 divided by 19.6 is going to be our height. So our height is going to be equal to 1.16 meters. Now, a bit of advice, so this is how the question is going to be answered. So you can use the form to do all of these different steps. And I'm going to go to this side just so that I can show you something. If I get something that says, say, 30 is equal to 10 plus, or how about this, 10v squared plus 6. Then if I'm solving for v squared, just beware, we are solving for v squared before we do anything with that square. So I'm going to have my 30 is equal to 10 v squared plus 6. First, I'm going to isolate the term with the v squared in it. So I'm going to subtract 6 from both sides. And then I have 24 is equal to 10 v squared. Next, I'm going to isolate my variable. Again, we're not touching the square yet, so divide by 10, divide by 10. And now I have v squared is equal to 2.4. Now, to find v, I want to take the square root of both sides. And that would give me a speed of 1.55 meters per second. So just beware when you have the v squared, you want to solve for v squared equals before you do anything with that square root.